microphone?
The dominant sensing modalities. A module that is very much self-contained, is not affected by other modalities. And in this talk, I'm going to argue that this is not quite accurate. And vision can be signals of other modalities in occasions very strongly. And this can already happen at a very low perceptual level. In that sense, we can consider vision as a multisensory process. Now, if you, for example, close your ears during this talk, not only you're going to hear my voice differently, but also it may affect the way you will see me. Now, exactly. And there's no need to do this throughout my talk, because I'm going to show you an effect, an illusion that illustrates this one nicely. This is an illusion we found a couple of years ago. We call it sound-induced flash illusion, and it works this way. When a brief flash, a single flash, is accompanied by multiple beeps, it's perceived as multiple flashes. Now, I am going to show you a demo, because I'm not sure how many people have seen the demos. And the cross sign on the screen that you will see shortly is the fixation point. And you need to keep your eyes on this cross sign, and you will see pairs of trials. And you need to pay attention to see if you notice any difference between the first and second one in terms of the visual stimulus, if the two are any different. So here we go. Another try. Okay, so no more tries.
The fire.
I think in the second one, the screen was blank.
Okay, so I'm going to try this again. Let's try this one more time. Okay, another round. Alright, so you probably see one flash in the first trial and two flashes in the second trial. And this is despite the fact that the two trials are identical in terms of the visual stimulus.
Do it slow.
One more try. Okay, if you don't see the effect here, you can try my webpage. There's a quick demo. This is not calibrated for this projector. But if you stare at what?
If I stare at this, it still works.
Even when you look at it
Maybe it's late.
because it's hard. Yes.
Do you have to put the flash in between the two sounds to get the maximal illusion?
No. Well, to get the maximum illusion, yes, it helps if they are aligned. The center of the signals are aligned. But the illusion remains strong within a window, temporal window of about 70 milliseconds or so.
We have one flash in the stimulus, two flashes in the stimulus.
There's one flash in both cases, only one flash, and I can prove this to you by turning the sound off and running the same program again. Now, the same thing. Now, you can see for yourself that the visual stimuli are identical. So all the difference between the two was caused by the sound. Now, we have done experiments and we found that through various observations and control conditions, etc., that the effect cannot be explained by a general attentional factor, eye movement, cognitive bias, and the only explanation for it is that vision is being affected by sound at a perceptual level. We have also found that the effect is very robust with respect to a number of parameters. You can manipulate a number of these parameters and still the illusion remains.
Why is it that when I'm listening to your voice, my visual world doesn't jump around?
Okay, so you need to wait until the end of the talk because that's going to be the second half.
Have you conducted such experiment on monkeys? Because I'm wondering whether for us, we could use it. Usually the deep and the flash work perfectly in our experience. That might actually explain this.
Let's hold the question.
We are doing monkey experiments. And so the effect is very strong and it's very robust, and this makes it an ideal tool to explore, to use this as a tool to explore auditory visual interactions in general, and to examine the mechanisms that may underlie these interactions in the brain. Now, so that's what we did. The next question we asked was whether the alteration of vision by sound happens at some higher order polysensory area, perhaps in the association cortex, or whether it happens along the visual pathway. So we did an ERP study. We used a classic flash Itti paradigm where we record from 3 electrodes in the occipital area. We record the response to flash in the visual field, and we introduce sound, in this case 2 beats that leads to the passage of this elusive second flash. Now, we replicated these conditions in the periphery and fovea because we had noticed that the illusion is much stronger in the periphery when the flash is in the periphery compared to the fovea. And we wanted to see whether we find a neuronal correlate to this. This is what we found. The red blocks are these intervals of significant activity or interaction. In the fovea, when the subjects did not report an illusion, we don't get any interaction. In the periphery, when there is an illusion, we get significant intervals of interaction. And we get similar modulation by sound as we get by adding a second physical flash. The pattern of activity is very similar, and this suggests that a similar brain mechanism underlies the representation of the elusive flash and a physical flash. And why is this interesting? Because a physical flash must involve the activity of cortical visual areas, and this suggests that the illusion also involves activity in the visual cortical areas. Now, we did an MEG study, a similar design, and we get similar results. We get very short latency interactions in occipital channels. This is an MEG with 122 channels. Now, to localize these areas of interaction more precisely, we did an fMRI study, again using the same paradigm, and we get these results. When we compare the bimodal conditions, one flash to be versus the visual condition, when the flash is in the fovea, then we get activity in the auditory areas, which is not surprising because here we have sound and here we don't. But if we compare the same thing, if we look at the same contrast, but when the flash is in the periphery and there is a strong illusion happening, then we get different results. We get, in addition to the auditory areas, we get activity in early visual areas, areas 17, 18, and 19. Now, if you hadn't been paying attention over the last couple of minutes, this should surprise you a lot, because it says that activity in the early visual cortical areas is induced by sound. And we find that this is indeed the case, and it does correlate with the percept. So here we also also have sound, but there is no illusion. We don't get such activity here. We have an illuminated activity. Now, we also find that there's a large overlap between the representation of the illusory flash and the physical flash. Here, the physical flash is shown in green and illusory one is red, and this suggests that, again, similar representation is involved in both illusory and physical flash. Now, you may ask, what kind of pathways involved in modulating visual activity as early as eras 17, 18, and 19? And interestingly, two very recent studies, neuroanatomical studies in monkey, have reported very similar results that can offer a plausible solution to this question. They report extensive projections from auditory cortex to B1 and B2. And even more intriguing, they report these projections to be concentrated in the peripheral representations in B1 and not in the foveal representation. And this is very consistent with all of our findings from physics to ERP to fMRI, where we find much stronger effects in the periphery than in the fovea. So these results altogether indicate that activity can be modulated in sound can modulate activity in visual cortical areas, and these visual areas are not as strictly visual as we used to believe. Now, the next natural question to ask is, what are the rules of the game? When do we integrate information from the different modalities? When do we keep them apart? And how do we integrate them? To what extent and in which direction? Which modality affecting which other modality? Now, to find out, to get some insight into these computational principles that may govern these interactions, we need a model that can account for data. Now, if you look into the literature, we find that all the previous models of cross-modal integration have assumed that the sensory signals are caused by the same source, by one source, and therefore they're always fused into one person. Now, this means that these previous models skip the first question of when not to integrate, and they move to the second question. Now, this may be reasonable for cue combination within vision, because the cues that arise from the same location, they're almost always corresponding to the same object. But in cross-modal integration, this is no longer the case, because we can have signals in our brain at the same time that could be originating from different events, and we should not, and we do not integrate them. So we decided to come up with a model that can address all of these questions at the same time in a coherent way. And in this model, we don't assume mandatory integration, therefore, and we use Bayesian inference as a core of the model to provide an ideal observer model that would serve as a benchmark that we could compare the human performance with. So this is our model. We assume a separate source for the auditory signal and a separate source for the visual signals, and these two sources may or may not be the same. And that allows us to both make inference about cases where there is integration and cases where there are segregation. This is a graphical model, which means that each node is a random variable, and each arrow is a potential statistical dependency between two random variables. And more importantly, the absence of an arrow represents statistical independence between two random variables. So here we are making two assumptions. One is that these sensory signals are conditionally independent, which is a common assumption based on the fact that, or the assumption that the noise processes that corrupt different pathways are independent. And we also assume that this sensory signal is independent of this cause, and again, I can get into this if time allows later, which is an intuitive assumption again. Now, these arrows represent likelihood functions, likelihood of the sensory signals given the causes, and there is a high probability associated with the causes. And this captures the perceptual knowledge that the ideal observer has about the world. What kind of events are likely to happen, what kind of events are not so likely to happen. So for example, the size of Pavarotti and Puccini opera is more likely than Pavarotti and hip-hop songs. So these high probabilities are learned from experience, but they can also reflect response biases that are due to the demands of the task, as well as hardwired biases that could be imposed by the neuroanatomy of the brain or neurophysiology of the brain. Now, the ideal observer at any given point tries to make the best possible estimate about what is going on in the world for any set of sensory signals based on these pieces of knowledge, likelihoods and priority. And makes this inference based on calculating the posterior probabilities of these causes. And this is done using Bayes' rule. And given our assumptions, we can simplify this into this inference rule. It simply says that the likelihood of these events, these causes, given the sensory signals, is simply a normalized product of the likelihood functions and the priors. Now, we tested this model using our favorite paradigm, the flash illusion paradigm. And we asked subjects, so we presented subjects with variable number of flashes and paired with variable number of beeps, and asked them to judge the number of flashes they see and the number of beeps they hear in every trial, 2 tasks in each trial. And here's the data. The red circles represent the auditory response of the subjects. The blue squares are the visual discriminations. Each of these plots is one of the conditions. The first column are the unimodal visual conditions, when there is only visual stimulus. And the first row are the unimodal auditory conditions, when there is only sound. And the rest are bimodal conditions, when there is both sound and visual stimulus. The horizontal axis represents the response category, 0, 1, 2, 3, 4, plus all flashes. And the vertical axis is the response probability. Now, in this happens to be a perfect paradigm to test our model because I'm 1 minute from finishing. Because it gives us a spectrum of all auditory visual combinations. We have conditions where there is full fusion along the diagonal. The 2 signals get completely fused. We have conditions where there is almost no fusion, and we have conditions in between. And the flash illusion can be found here, where the subjects are exposed to 1 flash and 2 beeps, and they respond in a large fraction of trial. They report seeing 2 flashes instead of 1. And we have also another strong effect here, where the subjects are exposed to 2 flashes and 1 beep, and they report seeing 1 flash instead of 2 flashes, which would be the greatest answer. Now, in the next slide, I'm going to superimpose the predictions of the ideal observer model on the top of this. So the squares and circles remain to represent the data, and the solid lines represent the predictions of the model. The blue line is the visual prediction, red line the auditory predictions. So, as you can see, the model fits the data remarkably well in all of the conditions. And I should point out that there are no free parameters in the model, and if we calculate the R squared over the 576 data points that it accounts for, we get R squared 0.87. So it fits very well. And these results show that the performance of subjects are remarkably close to the performance of the ideal observer. And this implies that brain uses a mechanism similar to Bayesian inference in order to integrate and segregate signals, auditory visual signals. And as a corollary illusion is not an aberration or a mishap of the visual system, but it should be viewed as a phenomenon of a general, statistically optimal computational strategy. These are my collaborators.
Allow one quick question.
Other illusion of functional now when the big shows the other illusions, have you tried other illusions than the one that you showed today? I want to see more other illusions of functional.
Right, that's on our agenda. We haven't done that yet. But I'm going to test it on other visual.
Have you considered a very simple subcortical explanation for this? That very moleculars, you get a correlation of transients with auditory visual. You maintain auditory visual maps, and it's primarily responding to transients, sharp changes. So you can get the ventriloquist effect where the location of a visual change seems to drag the auditory sound with it. And in this case, the transient through a beat gives you a beat, sensitive beats or transients in the visual map because they're connected. So that's what horizon has been showing. Where you broaden visual areas, there's simply be a feed-forward effect of that is consistent with correlating transients. And again, to give you events, so if you have transients in the real world, a visual and auditory, it's probably a single event that flows through time and space and so on. So I'm wondering, and you could of course apply a Bayesian model to the connectivity there, but in the calculus. So I'm wondering if you consider that as sort of an account of this illusion.
So, like you said, there is a very nice Bayesian model of integration with the superior colliculus as well. I don't think this effect is really happening with superior colliculus because superior colliculus is mainly involved in orientation and not in detection so much. And it does require spatial congruity between signals. And here we did the illusion even if the two signals are 90 degrees apart.
You get a ventriloquism effect that looks like there one can grab the other. But you didn't quite answer the question I had initially, which is, by and large, we don't want this. Because we don't want our auditory inputs to be affecting our visual world. It wouldn't be useful. You're hearing noise all the time, you're hearing my voice, and you don't want that to muck up your visual world. And it doesn't. So I wonder if this effect is really kind of limited to a case where you have some transients, and where it's useful for that to give you a boundary-mental perspective. But in general, it doesn't. There aren't this massive influence of auditory into our visual world.
Okay, so that's exactly what the second half of my talk was trying to do. That this is optimal. So the ideal observer model shows that this combination of audio-visual signals is indeed optimal. Even the illusion that we experience is optimal computationally. Now, you say that we don't want our vision to be modeled by sound, but we do want that because there is uncertainty in the visual perception, and this uncertainty can use help from other modalities. So the redundancy between the modalities, they can complement each other, supplement each other, and that will help vision. So it is a useful thing to have integration. And the optimal strategy is to integrate in certain conditions and to segregate in certain other conditions.
Okay, our optimal strategy at this point is to let Laurent talk for us, please.
Thank everybody for your
Thank you.
rounds to give out, and the first one was for the most novel idea. And let me just show you what the round is. It's going to be, so this is a prize. It's like a mini fridge that you can use in your office. You always have food. I don't want to be one of those. If I can now buy sandwiches and go work late at night and make sure that I still have food and drinks. So for the most novel idea in our first category, the lucky winner is Jude Mitchell, and that was from John Reynolds' group. The poster was by Mitchell, Stoner, and Reynolds. Object-based attention determines dominance in binocular rivalry. But the winner is not here, so we will shift. We will shift it around. It's the best-looking abstract also in the proceedings. You can't miss it. So that was our first one. Then we had another award for presentation, and this one goes to Debbie Dow, and the full author list is Debbie Dow, Dangling Lou, and Barbara Boscher for sine wave rating adaptation. Selectively reduces the gain of the adaptive stimulus. And Debbie is here, so could you please come and claim Laurent? So this was for the best presentation during the poster session. Welcome. And we have a last one, which was for the most complete results, and this is even more of a disastrous situation because it's poster number 19, but somehow I don't have a record of which number 19 was. Which means, so if anybody here wants to claim ownership, this is your chance. Otherwise, I would like to also thank Laurent and Jen, who has been doing a fantastic job.
I always like this number.
That's my favorite.
I would like to do a hand vote that we give the unclaimed prize to Laura, since we don't know who Congratulations, Laura. So thank you so much for coming again.
Just so you have something to carry.
Neuroscience building for barbecue. The last announcement is that next year this is going to happen at UCLA, and Dario Ringa is going to be the organizer for the 12th Joint Symposium on Neural Computation. Thanks again.